and now I'm happy to hand over to Gustav.
Thank you very much, Nina, and welcome from my side. And I hope you have brought some attention, because we are going to carry on similar to the last session and look at distance protection from a more practical point of view. The presentation today, as Nina said, is going to be a more practical application, in that we're going to look at an example, and I will focus also on the parallel line compensation a little bit, because during the first session there were a number of questions regarding parallel line compensation. The other subjects we'll get to in time. So without further ado, let's get right into the overhead line example. Now, when you are going to apply the distance protection to any situation, you have to collect the data. And obviously, as you can see at the bottom here, impedance data, this is for this overhead line, is very important, as the distance protection, impedance protection, will be working based on an impedance loop measurement, as we already discussed. The impedances you see here come in different formats, but you will typically find here, as you can see, R1, X1 or Z1, depending on how it is given, it doesn't really matter, is your positive sequence impedance. That is also going to be very closely related to the reach setting. For the ground faults, we'll look at that in more detail later on. You need the zero sequence impedance of the line as well. This can be given as an absolute total line impedance, or as in this case, you're given as a per kilometer impedance. And then you obviously need to know the length of the line. And from basically on this data here, we can really calculate most of the critical settings for the distance relay. Also shown is the tower geometry. From the tower geometry, as we know from the first session, the arc resistance is going to be calculated from the length of the arc, which we also base on the insulator length, or the separation of the conductors as seen here. And finally, what could and is very critical also is, how is your system grounded? As you see on the complete left over there, is it a solidly, effectively grounded system? Is it with resonant grounding? And the example we're doing today is going to be with an effectively solidly grounded system. For the Peterson or resonant coil grounded systems, obviously one needs to consider differently, because ground or single phase faults are not real short circuits, are treated differently on those cases. But that is a different subject. Today we are looking at effectively grounded systems. Another aspect then relating to that is obviously your instrument transformer, your CT-VT connection, as you see here. We need the data from the CT-VTs for the application, the ratio, and as mentioned in the first session, the conversion primary secondary is important. You need to check, and you can in Dixie, as you see on the complete bottom left hand corner there in the orange block. This time the setting there is applied as a secondary impedance. You can also apply your settings as primary, so very, very careful that you don't get that mixed up, because there is a difference. You have to convert the primary to secondary based on the CT-VT ratio. This is the equation you can use, where you can take the primary impedance here and multiply with the CT-VT ratio as shown, and then the result would be the secondary impedance. That's important, okay? The other aspect we come to now is a little bit more general. CPROTEC 5 application or methods of implementing relays. Not really going to this in detail. This is, if one is new to CPROTEC 5, maybe one should do a Dixie type course, which will explain all the steps necessary. But just quickly speaking, you can see here, and this is if you apply a new device in your Dixie, you enter at the top either a short or long product code. What you see at the right at the top there is a long product code. You don't have to type that off by hand. Normally you'd imply that copy paste, or you would enter a short product code. That is the hardware description of the device, okay? It's basically what you have purchased. And if we do this, we basically make an offline version of the relay, or basically a Dixie-based version of the relay. And the next step, that is just a piece of hardware at the top. So when we implement it in Dixie, we have to typically choose at the bottom a template. And the template you can take from the standard library. And you can see I chose in this case for not a breaker and a half, but a single breaker, solidly grounded system. And I choose the firmware version, and then you can apply that. If you do this on a regular basis, then you would obviously have your pre-configured starting configuration which you want to use, and you can use a user-defined template as well, which is very helpful to simplify the engineering process. But that's not our subject today. We are talking about distance protection. So let's move on to the next thing and try and find where is the distance protection located now in the device. On the left, you see that is the project tree that's also shown in Dixie. And in that structure, you'll find there is the function group. You see the function group line there. And inside that function group line, they would find the distance protection about 5th or 6th from the top in the function group line. You can see it there, 21 RM distance protection. That is implemented there. If you want to apply a classic or another one, you can delete it there and from the library add that to that, or if there are, but also from a template point of view, delete, because you see there are a lot of functions there and you may not need all of them. Delete the ones you don't want and configure your device as required. That is that point. The other thing that we did see, we have to always see the CT-VT connection. That is shown in the other templates here, is another key aspect for the relay. If you're going to apply that, you have to obviously make sure that the CT and VT is connected to the function. That is done in the Dixie configuration under the measurement point routing. And you can see here, physically in the middle, that would be the current measuring point. So I have defined here 2 current measuring points. It's interesting, the one, a 3-phase current measuring point, that is going to be the one connected to the protected line. And as mentioned at the beginning, we want to look at parallel line compensation. So if we're going to apply the parallel line compensation, we also have to measure the ground fault or residual current from the parallel line. And that's what the second measuring point, you see it's a single phase measuring point current is applied here for at the moment, just as IX. You don't know yet that it's parallel line. It is just a measuring point at this point. It is nothing more than that, right? And also important, if you have to really work with a relay on site, you don't need to refer to any manuals or pamphlets to find the terminal numbers. In Dixie, you can see the terminal number of the device at the top here. There is the actual physical terminal and the IA phase current is connected there and so on. And the parallel line residual current, as we'll see later on, is connected to this terminal here. At the bottom, the voltage in a similar manner. There also a 3-phase measurement for the line and a single-phase measurement probably for a sync check, maybe a bus bar voltage for sync check. Not a subject we'll cover today, but I just showed it there for you to see for completeness. All right, that is, I think, Dixie configuration as you would do it. This is a graphic representation, maybe easier to explain, to re-emphasize what we just looked at in how you do it in Dixie, just a picture of that. At the bottom, you see this diagram, and in this diagram, you can imagine that the outer block, the gray block here, is a physical device, and the physical device would have terminals to the outside. Here you can see here binary input outputs would be binary inputs and outputs, and so for the trip signal to the breaker, maybe the close signal to the breaker, feedbacks for breaker auxiliary status, and so on. And on the complete left, you see also terminals to the outside. That would be the current measuring point and the voltage measuring point. And those we have just assigned, remember? And to those terminals, remember what we said there? And those are then internally considered as a logical measuring point, which is then routed to the function group. Remember, our distance protection was inside the function group line. And you see that middle blue block there. In the middle there's the 21, our distance protection, and it derives its measuring point from this function group line. And as I say, the logical measuring point current, completely on the left there, is used in both function groups, the function group circuit breaker and function group line. The trip command that we route out, and also the feedback, the status, because there are functions in the line that need to know the status of the circuit breaker, that you don't derive that directly from the outside. Here you derive this via a function group circuit breaker, because all the logical devices like auto reclosure we'll see later on, those are not implemented inside a line, those are implemented in the circuit breaker where they belong, like a sync check function, auto reclose, breaker failure, and so on, are done inside a function group circuit breaker. And the trip command of the line goes to this logical circuit breaker, and the circuit breaker then processes that onto the outside. This is the structure of CPROTEC 5. But I think that's enough of that CPROTEC 5 structure. Let's get back to the distance protection. And one of the key settings or things that one has to remember in distance protection is the so-called residual compensation factors. It's a name. Maybe you know them better as KR or KX here. Also, sometimes CPROTEC 4, you might know them as RE, RL. Well, I showed it here, RE, R1, XE, XL, or XE, X1. Your residual compensation factors, as we know that. Why can I replace R1 and RL? And you see it in the diagram here. You see that the impedance, as it is shown in the three phases there, is the ZL, which is RL plus JXL. That is your positive sequence impedance. For it to be a positive sequence impedance, that is our assumption, is that those three-phase impedances are exactly the same and balanced. That's the definition of a positive sequence impedance, and that then can be substituted directly. So we can replace that RL, XL, in this case exactly by the positive sequence R1 plus JX1, the definition. So what am I trying to show in this diagram? In this diagram here, I connect my three phases with a short circuit at the end of the line, so to speak, and I inject at the beginning 3 voltages, and the 3 voltages I inject are those 3 blue arrows. They are exactly in phase and identical. So if in that case, what voltage is that? That is the zero sequence voltage by definition. But the zero sequence voltage means that it is exactly the same in all 3 phases, magnitude and angle. That is a zero sequence voltage. What you could do in this case, you could make a short circuit here because the voltage there is identical and replace that injected voltage with a single U0 zero sequence. All right, what else can we derive from this diagram and what this diagram is used for? Because with this diagram or this connection, you can measure the zero sequence impedance of the line. And this is then done in a reverse technician because you have a definition. As you see in the block there on the left, definition. The definition of the zero sequence impedance is U0 divided by I0. So that is our definition. So with this circuit then and our test conditions injecting there, we then can make this voltage loop equation in our classics way and go around one of these paths, just one, you don't have to go around all 3 of them. You can choose any one, but they're all the same. The injected voltage is U0, and then you go through an impedance here, which is your positive sequence impedance, ZL. Remember ZL I said was your positive sequence impedance. And then you come to the bottom point here, but here be careful. There are 3 I0s coming down here. Each one will have exactly the same current because it's balanced, as we said at the beginning. So you'll have exactly I0 plus I0 plus I0. So you'll have 3 I0 coming down here and flowing from right to left back to the source side. So if you make a loop equation over there, it'll be I0 times ZL is the voltage drop here, and 3 I0 times ZE would be the voltage drop here, and that is going to be equal to U0. Be very careful with your signs over here, with the plus sign. Remember here, if we were using IE instead of 3 I0 here, it would be a minus sign, because remember IE is equal to minus 3 I0. It has to do with the direction, because the arrow, as you see over there, is defined the current flow for IE, positive always in the direction of the protected object, the line, but the I0 is flowing in the opposite direction from right to left, so that's why IE equals minus 3 I0. But for the loop equation, this is the correct way to do that. Taking the definition and substituting this for the U0 in the definition, you then get this bottom equation here. And then if you divide the I0 into the top, you get the simple equation at the bottom there. Very interesting. If you look at that, Z0 equals Z1 plus 3ZE. What can we derive from that? We can see from that that Z0 on an overhead line can never be smaller than Z1. On cables, the ZE can be a bit strange, depending on single phase or 3-phase cables and so on. But if we look at overhead lines, the ZE will always be similar to, well, larger than the Z1 even. So the Z0 cannot be smaller than Z1. That's very interesting. All right. Rewriting that equation, following the orange arrows, we then come to this equation here. We can then derive ZE, and this is an important thing that I wanted to say in the diagram at the top. Remember, we said this was Z1, but this is not Z0. This is ZE down here in this diagram. Be careful to relate to basically get from Z0 to ZE, you have to use this equation. Z0 minus Z1. Right, and then from there on in, we can calculate this RE, R1. Remember, R1 is the same as RL, as such, the Kx over here. And we derive these two equations from that. Why do we need to do this? Okay, so it seems like we're calculating two factors here, the Kr and Kx effectively as they are known in CPOTEC 5. Why did we do this? And we did this because, and here we are showing from the manual, the classic ground loop or ground fault calculation formulas, the method in which the X is measured during a ground fault or the R is measured during ground fault, the way the impedance is measured by the distance protection for ground faults. And you can see in those formulas, the Kr and Kx factors appear a number of times, not just once, they appear a number of times in those equations. Why do you use this rather intricate method? Because on the left-hand side of these two equations, what you see there, the measured impedance is the positive sequence impedance. So we can apply the same reach setting. Well, later on we'll see we'll apply reach settings, and we then no longer discuss is it for a ground fault, is it for a face-to-face fault. It doesn't matter, because both the face-to-face faults and the face-to-ground faults will measure an impedance which is basically the same. It is the positive sequence impedance, or as shown here, the loop impedance. And the setting, we can therefore apply the settings, the reach settings based on positive sequence impedance. Okay, having done that explanation, now we come back to our example. Remember the example, we had the data given here for the line, the 60 kilometer line with these impedances. And now we can substitute, we derived the equations on the previous diagram. We can substitute the impedances here into the equation. You can see I substitute the R0, which is the 0.165 over here, and the R1, 0.028 over here into the equations we derived, and I can calculate the Kr and Kx, and then I would set that in the relay. And the similar for the Kx, that is that setting. So that we have dealt with, that's the first one. Interestingly, at the same time on that diagram, the line angle was set and so on. Those are standard settings you need to apply. The line length was set here, that's for the fault location, is interesting. And also the impedance per kilometer in primary was set here for the fault location. Right now I'm going to jump into the parallel line discussion because it fits in there a little bit with the Kr, Kx settings and so on. And then, let's say after the break, we'll carry on with the zone grading. So for the parallel lines, there is a modified loop equation, because the influence of the parallel line, as shown over here, is going to add an additional voltage drop when you do your loop equation. Okay, and this coupling that we have shown here really only exists in the zero sequence. Why only in the zero sequence? Because if you consider the three conductors under normal operation, they will have a current flowing out and back. And if it's a phase-to-phase or three-phase fault, then the sum of the currents of each line will add up to zero, because the current will flow out on phase A, back on phase B, and it'll be, if you capsule that, it'll be effectively zero. But if you take a ground fault, the current is flowing out on phase A and coming back via ground. And the ground, you cannot just bundle and sum up like that. The ground will couple into the other system. That's why in the zero sequence or in the ground path, we have a significant coupling due to this parallel line factor. The diagram we see here is typically used for the explanation. It's a parallel feeder end to end. Both sides, the bus bar on the left and right, the two feeders are coupled. And what you would then have typically, if you have a fault towards the right-hand side over here, you'll see something similar to this, that the ground fault on both lines will flow towards the fault location. So obviously on the faulted line, it'll flow to the fault location and then back. And on the parallel line, it'll flow towards the fault location via a remote bus bar and then back to the fault. So for the line is seeing the fault close to the remote end where you could have the risk of overreaching. Because remember, if the fault is close here, then we are not going to get overreach this side. But if the fault is close to this bus bar, the mutual coupling could make an overreach, and we need to be careful. So for the remote faults, we typically have this condition. Now, under that condition, the IE and the IE parallel line have a similar direction. Okay, so if we look at the voltage loop equation over here, they will affect the voltage in the same manner. And you can see both factors are minus. The three terms in this bracket over here, the first one is IA, and then you see minus ZEZL, that is basically K naught, or the KR, KX combined as one complex factor. I didn't want to write it out in KR, KX, then the equation would become unmanageable and not easy to recognize. So this is a simplified way of showing that, and also used with a complex calculation, even used an RMT method. You can use it. If you do a complex calculation here, this technique is still the same as the other one. But you see the first two terms would be without the mutual coupling. That is our classic line. That means we have no parallel line over here. Adding the parallel line adds this additional term here, and you can see it is also a minus IEP times this factor here. So if the IE parallel line and the IE have the same sign in the equation, they will increment the voltage. Okay, and remember what we did during the first session. If we have incremented voltage, the distance protection will underreach, it will not overreach. So the parallel line influence, as shown over here, will have no overreach. Okay, it will basically, so you have no risk of non-selective tripping under this kind of condition. So normally the parallel line is not going to be a critical thing in terms of overreach. You'll tend to see the fault a little bit further away. You'll have an underreach a little bit. However, there can be constellations where maybe the parallel feeder is open to that point, or sorry, the protective feeder is open on this side, and the fault current will come from here, down here, and round the loop back here. Not so serious, but if the breaker is open here, you cannot overreach. Okay, so also conditions like that are not critical. But the one shown at the bottom here is a very interesting one. If the parallel line is taken out of service and grounded at both sides, if you take a line out of service for maintenance work, etc., you would typically, for safety reasons, apply a ground at both ends. Then it would look like this. The protected line would be in service, and the parallel line would be out of service and grounded at both sides. If we now get the fault close to the remote end, or even the fault on the bus bar here, which is the critical one, then you'll see something interesting will happen. You'll get a current flowing, zero sequence current, or IE, flowing out on the line, and on the parallel line it will couple and flow back in the opposite direction. It is coupling, so the mutual coupling will make a circulating current flow here, and that current is flowing opposite to that one. And that would create an overreach. So during the parallel line open and grounded condition, one must be careful. One may have to apply some settings to reduce the reach, or, as we will show now, we have the option to apply a compensation. So this is the parallel line background. Interesting, if you look at this equation, we'll come back to that in a little while. It's a loop voltage. You can use that at any time to calculate the voltage drop on the protected line during a fault with a parallel line coupling. For the compensation, as we said earlier on, we have to measure the residual current of the parallel line. So you can see in this diagram now we have two relays and two feeders, line 1, line 2. These are two parallel lines. And what you can see is for the one line, you have this protected relay. It's measuring the currents from its CTs over here. And on at I4, as we did at the beginning, remember that was our IX routed as the fourth current input. That is connected to the parallel line. It will measure here the residual current, the return current from the parallel line, the IE of the parallel line as such. At the top you can see now that's actually that previous equation, the voltage loop equation, extended now into the KR, KX method. So you can see it gets a bit longer, but it's essentially the same thing. You can split the real and imaginary components as you've shown there in the two tops. That's the same voltage loop equation there, but not written with Z's, but with R and JX as such. From that, you can now see that that R naught divided by 3 times RL, that is going to be our mutual coupling or KMX factors. Similar to the KR and the KX factors, you calculate if you have a parallel line a so-called KMX, that is for the zero sequence mutual coupling consideration. And then we can rewrite the equation at the top and substitute the ratio ZX naught 3ZL, we can substitute with the KMX, KMR. And the important thing obviously is if we then rewrite this, we can calculate the impedance. So the impedance calculation equation we saw early on are then modified to consider the parallel line compensation. Okay, that is the connection we did, and this is now just showing you how it was implemented in Dixie. Remember, I had my parallel line current was the I4 current here. That was this one. I assigned that to that point over here, and that you have to. That was our mirroring point routing we did early on, and now interesting here in the function group connection. Remember, we had the blue blocks, which were the function groups. You were connecting your function group line to the CT. Here, this is this CT over here. Remember, this is this CT over here, the top CT, the three-phase CT connected here. And you also then say parallel line current, also connected to the function group line, is that single-phase current from the parallel line. And rename it. You can see on the complete left, I renamed that current measuring point I, one phase, IE, line 2. So you know it's the line 2 IE current, for example. You can rename it as you desire. That's important. So if you've done that, if you have a parallel line current, then you have the option in the settings you see at the bottom here to set that KMR and KMX, which we have calculated at the top. Your data of the line obviously is then expanded. You need to have additional to your positive sequence and zero sequence impedances. You also need your mutual coupling impedance values here so that you can calculate those data at the end. And this I did in an example. This is a different example. The previous example was a 400 kV, doesn't matter. For the parallel line, I used here 110 kV with slightly different data, but it doesn't matter. It's the same thing we do in application on 110 kV line. Okay, and having done all these settings, you then can apply that. And the question you could have now, is this all correct, what I have done here? Okay, so what you can do, obviously, is trying to use an Omicron to test that. Maybe if you don't have an Omicron, there are other options. You can use the so-called digital twin, and that's what I did. Applied the settings to a digital twin, and then calculated some currents to be injected here to see if everything is working. So here you can see this is a setting also under the distance protection. You have to say apply parallel line compensation yes. So then you actively say you want to use the distance protection with mutual compensation. Okay, what I then did, I took Excel. You can see there's the results of my Excel calculation. I take this equation. It's not so difficult. I mean, if you're interested, I can maybe make available the Excel calculation sheet in the download area. It's not very complicated. I used this equation and I created some fault locations. You see I took maybe 60%. I took two faults at 60%. I made M 0.6 times the line impedance, and then I defined a current. I think it was 3,600 amps for the one case over here, and then the IE would be automatic. So in this situation, I keep things simple. You can see there's no fault resistance or anything in there, and then I assume that my IE is going to be equal minus IA. Just make a normal. Otherwise, you have to make a more complicated injection. But so I just inject an IA current, and the IE will be minus IA. So it's a simple loop in the protected line, and inject in parallel an IE parallel. And you can see that's the results you see over there. Test case 1 is the top line. I'm injecting a current 6 amps over here on the protected feeder, and that would mean it's minus 6 amps IE on this top feeder, and the parallel line current was 0. So that would the parallel line current just out of service, not working. That was my first test case, just to make sure that even without the compensation, everything is working. So it would just be the calculation as you see there, IA K0 times IE. And then for the second test case, I now inject the current IE in the parallel line, 4 amps at 180 degrees. What case is that? That is this case over here where the IE and the IEP are in the same direction for the second test case. Remember, because I'm injecting 5 amps, as you can see, into IA at 0 degrees, that means the IE on the protected line is 5 amps at 180 degrees, or minus 5 amps coming back the other way. So the 4 amps here, that means we have in this second test case 5 amps here and 4 amps over here, and the 4 amps and ground currents are parallel. Normal application, remote fault, and again it was at 0.6, just to compare the two results. So both the first two faults are both at 60%. And then finally I did a case for the bottom here. I moved the fault to 85% in that case here, and I injected 6 amps on the top feeder and 5 amps in the bottom, but the 5 amps in the opposite direction. And it's interesting, if you look at the voltage magnitude, although the third test here has 6 amps and 5 amps in the parallel line, you can see the voltage on the complete left is only 45 volts secondary for the third test. Although it's larger current, normally larger currents would give us larger voltages. If you compare it to the first test was also with 6 amps on the protected feeder, and it was 46 volts. So the 5 amps on the parallel feeder actually reduced the voltage. That's what we expect. And that's the risk that this final case can give you an overreach. You can see we have the same current in the third test as in the first test on a protected feeder, but a smaller voltage. So we would, and the fault is further away. Remember, for the first test, the fault was at 60%, gave you 46 watt, and for bottom test, the fault is at 85%, and you still get a smaller voltage. That is the significance of the parallel line in feed. All right, so I tested all those with the digital twin. All right, and you can see the screenshot. That is not a photograph I took of a real relay. That's a screenshot from digital twin. And on the left, you can see that was similar to an Omicron. What's it called? The quick CMC. You just inject 3 voltages and the fault current. You can see that's my first test case with the voltage. Be very sure to put the right angle in, that 77 degrees, and then the 6 amps on the IA phase current. And at the bottom you see 21 kilometer. 21 kilometer is that 0.6. Remember the line was, I think, 35 kilometer line, I think. I can't remember exactly, something like that, but that works out. The 21 kilometer is exactly what we expected. So for the normal case with no current in the parallel line feeder, so IEP is 0 during the first test, we get the expected result here, 21 kilometers. So those settings are correct. Now we do the second test. We now, again at 60%, but we apply a parallel line current right at the bottom. You can see 4 amps, and the 4 amps are in the same direction as the IE on the protected line. So 5 amps on the protected feeder, and 5 amps coming back, IE on the protected feeder, and 4 amps on the parallel feeder. And again, you can see the fault locator. Remember, this is the fault locator. It's not really distance protection, but the fault location and the distance protection are both using the compensation at this point. So at least the fault location indicates that we have done everything correctly for that test. And then we do the third test. The third test is at 85%. That should be 29.75 kilometer. You can see it came out correctly. And for the third test, you can see the IE on the parallel line is in the opposite direction to the IE on the faulted line. Small voltage, and yet the impedance is furthest away from all tests so far because it is obviously at 85%. It works correctly. Then finally, what I did just to check something is, over here we did just a relook at this case over here. This fault should be seen in zone 2 and not in zone 1. And if one looks here carefully, you can see here it was a zone 2 operate for that second case. And the fault location is at 29.8 kilometer where we expected. This is the fault log for that test case, just to show there's a correct zone 2 operation, not zone 1. So distance protection did not overreach. The fault was seen correct at 85%, did not come into the 80% zone 1 setting. So that proves that also the distance protection is working correctly here. Only a zone 2 operate, no zone 1. And the fault locator there is also working correctly. What I then did as a final check quickly is to disable that. You can go into the settings, and in the settings you can switch off. Remember we saw the setting early on where I said apply mutual compensation yes or no for the distance protection. Didn't change it for the fold occasion. So you can see I retested that test 3, the one at 85%, and you can see the result. The fold locator is still showing the 29.8 kilometer, but because I disabled the parallel line compensation for the distance protection, you can see it was a zone 1 operate. The impedance moved into the zone 1. So you can see the importance, if you're going to apply that, to do it correctly. But if you calculate your parameters suitably, you will get a good result as that. And that's a nice way of checking that. And the digital twin, I can recommend that if one wants to simulate something like that or check it, it is a nice way to confirm that your settings are done correctly. Yes, so I'll come back. Now we carry on to the distance protection classic conditions, the setting and the zone grading. Back to our original example, the 400 kV with the 60 kilometer line and those impedances, we are going to now calculate the R and X setting for the zone 1 and then later on also show the zone 2 conditions. So the first thing we're going to do is do the resistance. And for the resistance, we are going to need the arc length as shown there, 5 meter for the single phase. That's over one isolator string to the tower, the 5 meter length, and for the separation of the face-to-face conductors is 12 meters there. With that, we can calculate the arc resistance, okay? And for the ground faults, and I'm going to focus on the ground fault. Remember, for the face-to-face fault, we only have an arc resistance. There's obviously no tower footing resistance. It's just that 15 meter separation face-to-face is relevant, not the tower footing resistance. But for the face-to-ground fault, it consists of two factors, the arc and also the tower footing resistance. And the sum of those two is the effective RF that we need to consider for our setting. So to take the examples here, we take those 5 meters and you substitute that in this equation. This is what we also showed in the first session a couple of weeks ago, the arc resistance, so I don't want to spend too much time on that. We use a 2,500 volt per meter arc voltage. That's fairly conservative. Typically voltages will be smaller than that. Okay, that's on the higher end, so we don't really need any additional safety margin. That is a very, very conservative, in other words, a large estimation of the arc resistance. One does not need more complicated things like Warrington equation. There is not really any gain because at the end of the day it's a large uncertainty. The 1.5 is a factor because the arc will typically not be in a straight path, so we don't just simply use the 5 meters, we extend the 5 meters by a factor 1.5 to make allowance for the curvature of the arc as such. And then you need to obviously know a fault current. In this case, this is the fault current as measured by the relay, not the sum of the fault currents from both ends as such as we need for the tower footing. Here, because remember the arc voltage is a voltage, and we simply going to measure that voltage, and that voltage and impedance, as for us, our relay is just going to be that voltage divided by the current that we are measuring. So relevant here, that fault current is the local in-feed fault current to the fault. For the tower footing resistance, again, as not done before, there's a number of, in parallel, the current will go flash over to the tower and then it will separate along the ground wire and come down on parallel tower footing resistance. So we don't look at one, it's basically a combination of those in parallel. And we use, example, this graph here will give you some typical values for a single or a dual earth wire. And this our tower, it's a single earth wire, so we on the blue curvature. And then based on what each tower footing resistance is, you can estimate a resistance of about 2 or 2.5 ohms for the tower footing resistance. All right, and we calculate that in our case for the tower footing resistance. At the bottom, you can see the arc resistance, first, the 6.25 ohms there. And we do that with a 3 kiloamp in this example for the local current. And for the tower footing resistance, as I said, you have to consider the remote in-feed as well, because it's an ohm. It's now a resistance like Ohm's law, and the sum of the currents must be considered. So we have to summate those two, the 2 kiloamps from locally and the 1 kiloamp remote, There'll be 3 kilograms flowing through the resistance, and we will only measure with 2. So we have to basically apply this remote in-feed consideration. So the 2 ohms tile filling resistance that we extracted from that graph over there is multiplied by this factor and actually are used in the equation as a 2.5. It's interesting, if the remote current were also 2 kiloamps, then we would multiply by 2, then we'd have here 4 already. So the remote in-feed is very, very significant in terms of the RTF. It's not something I'm covering here in this presentation, but it's something specific. If you have weak in-feed constitutions, you may have to, in terms of the resistance, consider successive sequential tripping considerations, because you cannot obviously apply here a ratio of 10 kiloamps from the remote side, 1 kiloamp here, then you multiply this by 10, you end up with 20 ohm arc resistance here, and very big settings will come to symmetry later on. One has to be a bit conservative. All right. Then to set it, we would summate those two to get the fault resistance, and then again it's important to check if we are using a classic distance protection as we are doing here for the ground faults. In the classic, the RF is divided by this factor 1 plus KR. Why is that done? I'm not going to go through it in detail now. I think we did that in the previous presentation. It is because the equation that we're using to calculate the ground resistance as shown early on with those factors extracts the positive sequence impedance. Remember, we have here the loop current will be the ZL out and the ZE return, but measured and applied in this curve here is only the positive sequence impedance. So this resistance here is not part of the positive sequence, it's not part of the E, it's somewhere in between, and the way the method of measurement deals with it, it separates it into one portion into the positive sequence and one portion into the ZE. And that separation factor is this 1 plus KR. So what actually appears in the measurement with the classic is not RF, but RF divided by 1 plus KR. So that is what we must use in the setting when we are going to set the resistance reach for the classic. And you can see in the green over here, that's where I calculated that. The 1.2 is a 20% safety factor. So 1.2 gives you a security that you would definitely see the resistance. And then you multiply that, the sum of these two resistances as we calculated them on the previous slides, and divide it by that 1 plus KR. Oops, sorry. I wrote KR in the equation, but over here it should be divided by 1 plus KR. Actually, that's actually a mistake I just found. Ooh, so you see, even there, you can do mistakes, and you just see me. It should have been divided by 1 plus KR, not just by KR. Okay, so even smaller setting. That would be then applied there, and for the phase-to-phase, you would have to then take the 12-meter arc resistance, because only arc resistance is considered for phase-to-phase, the 2,500 volt per meter, 1.5 safety factor, and for the phase-to-phase, we consider 3 kiloamp as a local in-feed for a phase-to-phase fault, a slightly bigger current than on the phase-to-ground fault, and that gives us 15 ohms setting for the phase-to-phase. Well, I think that should also be divided by 2, but never mind. Okay, so the setting for the zone 1 reach now, this is the X setting. The X setting is calculated basically at 80%. Our typical zone 1 safety margin, as we discussed also in the previous, that you need to consider on the complete measuring chain, CT, the instrument transformers, the relay, and also important, your line parameters can vary. Also seasonal variations, wet days and dry days can have different line impedances, especially in the ground loops. Hot days and cold days, it's not huge differences, but there is always going to be some tolerance. Your measurement is never that perfect. And we use 20% typically. That's why I only set to 0.8, not to 0.9 or 0.99, to make sure that the zone 1 never overreaches. That was our discussion during the first training session when we said the zone 1 is an underreaching zone and may under no circumstances trip for an external fault. And that 20% safety margin is what we use for that purpose. You can see here the remote bus bar, and then we set 20% short of that, and that makes sure that we will never see an external fault in the zone 1. That is our grading here, and calculate it like that quite simply. But as I think mentioned in the first session, we now cannot just move on. We have to now, before we finalize this, check the symmetry. And the symmetry condition has to do with the measuring tolerance, as I mentioned that, because we have got tolerances, and the 20% safety margin must consider that and must obviously be larger than our tolerance. So I just made an example and say that the 20% safety margin we apply was used to take into consideration a real tolerance of 10%. That means, but if you look at the 10% tolerance on the impedance, you see the circle radius here is showing the tolerance. So if the fault is here, due to 10% tolerance, it can be anywhere inside that yellow circle. And as you get closer to the other side, the impedance gets shorter and therefore the circle radius gets smaller. But what is the problem? If this encroaches here, that means surely that with a 10% measuring error, you could see the fault inside the zone 1. Although this is a 20% tolerance, remember that is only calculated based on the X. So this is 20% tolerance on X, but if you take the Z is twice as long. That's why the 10% tolerance comes into the reach. And that is obviously unacceptable. You don't want the zone 1 to reach in it. It's an example. Okay, the real tolerance problems are not as much as 10%. They are way smaller than that, maybe in the order of 5%, and one can live with that, but this is just a graphic form showing that why one needs to consider this carefully. So let's check what was our result. So in our case, we have set here 7.5 ohms was the requirement on the R setting, and for the X setting we had 16.8 ohms. So we are at a ratio smaller than 0.5, so we are really on the safe side. You can see way on the left here, very safe. And if we look at the table that we use as an orientation from the manual, you'll see that for a line here, remember we have a 60 kilometer line here, and for that we can orientate here that we should have a ratio somewhere between 1 and 2. This is not a rule, it is just an orientation guide. But if we are at 0.5, then we're going to say, all right, that is maybe a little bit small. We will just increase the R reach until we have a ratio about 1 to 1. That would be what I would recommend. So increase the R setting there to about the same as the X. All right. That's the end of the zone 1. Let's now look at the zone 2. The zone 2 setting has got a different requirement. Remember, the zone 2 is our overreaching zone, and the definition in the name says overreaching. It may not fail to see an internal fault. So there we apply a 20% safety margin again, but this time overreaching. So you can see it in the factor there as 1.2 times the line impedance. So we have, as you see at the bottom there, a 20% safety margin, but overreaching. So we have to set it to 120%. That is the requirement. That's what we will set. You can maybe on short lines say maybe set it 150%. It's fair, but it must be at least 120% under typical conditions to give you that minimum safety margin of 20%. The other boundary you see now, and there is another boundary for the zone 2. The zone 2, in terms of our selectivity concept, may not pass or encroach beyond this zone 1. So let's have a look at this little graph over here. Our protected feeder is the one on the left with the R line and plus JX line over there. And then we have the remote bus bar over there. That's up to where we must reach, and the zone 2 must reach beyond that. And then on the next bus, on that bus bar, we have other feeders. And the one we need to worry about is the shortest feeder. The shortest feeder coming out of the bus bar over here on the right-hand side. That shortest feeder is going to, in our concept, have also distance protection, and that will have a zone 1 setting. So on that shortest feeder, and this would be this one over here, you can see it's shorter than the one on the top. That's our shortest feeder. It has a zone 1, this blue zone 1 over here. This blue zone 1 is a setting of the distance protection on this feeder here, the remote bus bar side, outgoing feeders. Our zone 2 may not pass this point. What will happen? What will happen if our zone 2 picks up for a fault over here? Then we will run our zone 2 time, and what will happen? This zone 1 will not trip. So what will happen? The zone 2 on this feeder and our zone 2 will probably trip simultaneously. And non-selectivity, a loss of selectivity or a bad grading condition. That's why we again apply our magic 20% safety margin, but this time back from here. You can see that over here. So we must make sure that our zone 2 does not encroach into this boundary here. In other words, conflict with the zone 1 here. We grade always a zone 1 with a zone 2. So our zone 2 is graded with this zone 1, and it must not overreach this zone 1. So we have to go back here. And remember, this 20% here is not calculated with this feeder impedance, but with the loop impedance as it would be seen by our zone 1. Okay, so we grade. That's where you can see this 20% here is a significant portion of this line can be that 20%. So if that boundary is over here, then you can see, all right, we have here a little separation. I'll say we have set this value here, and that value is smaller than that value. We have a separation here, so we are okay. That's why it says okay. If this point here had been beyond that, we would not be okay. I did not show a graph like that. Then what you have to do, you'd have to increase your zone 2 time grading, one time grading step. Okay, which is a good point because time grading step, that is our next subject. All right, so just to conclude, we are going to apply the fault resistance settings based on arc resistance over here and the X setting based on the tolerances over there. But before we conclude, we must remember that the R fault we are using here for the setting is going to be different in the RMD, because the RMD for the phase to ground and only for the phase to ground loops. For the phase to ground loops, the RMD technique, remember that is not the classic, the alternative to the classic distance protection. The RMD protection is using a different way to calculate the ground fault resistance, only that one setting. And that one you have to then apply directly. And for RMD, you set it directly. You don't divide it by KR. You set this RF directly. So the 10.5 ohms here, calculated here, is basically 120% of this RF arc over here directly. That's a small difference. That's where the RMD setting is different to the classic. And also from a symmetry point of view for the phase to ground setting, therefore on the RMD you can approximately double the symmetry. So for a classic you would have basically the 1 to 2. For RMD you can use the 2 to 4. You can double that tolerance, but that's another subject. All right, time grading. What I wanted to get to. Time grading is something that when someone just accepts that, okay, my time grading step is 250 milliseconds or 300 milliseconds or something like that. In this example, we're calculating a 250 millisecond time grading step. But where does that come from? Why do we use that? And obviously we know we use that as shown here in this diagram again. For example, for a zone 2, that the zone 2 will not trip before the zone 1 on the remote bus bar has cleared that fault. You can see the fault there, the red fault arrow there on the single line diagram. External fault, our zone 2 at the bottom in that 21 relay is picking up on that fault, but its time delay will run, and typically a zone 2 time delay will be 250 milliseconds. And before that time expires, the top breaker will have opened and removed the fault. Which brings us to this diagram where we can maybe explain that a little bit. So at the top you see the red arrow, that's time 0, the fault inception. There's a pickup delay. All the relays must measure. They will not instantaneously pick up when the fault appears. There's a small measuring delay. The measuring delay is very commonly 20 milliseconds or shorter. I just showed it as 20 milliseconds as an orientation over there. All relays will have something in that order. Maybe they're a little bit faster. 10 milliseconds, the zone 1 trip can be even faster than that possibly, depending on the context you are using and so on. But it doesn't matter. That's just an orientation. For our time grading, we will use this 20 milliseconds as a general pickup time. The zone 1 at the top will then, after 20 milliseconds with a 0 millisecond time delay, immediately give a trip. So after that 20 millisecond pickup, what is now happening? You see the breaker time here. That is the breaker opening time of that circuit breaker CP1 at the top there. It's while it's opening. And that will take 2, maybe even nowadays 1.5 cycle, 2 cycle breakers In that order, what you can see, I took here 1.5 cycle breaker, 30 milliseconds, a really fast breaker. It could be slower, 2.5, 50 milliseconds, doesn't matter. When that breaker is then open, obviously the fault is removed and our zone 2 will drop off. But again, you have a drop-off delay. For the drop-off delay, I took 25 milliseconds, something in that order. So at that point, you can see here, we are safe. Our zone 2 has dropped off and we will not trip. The bottom relay will not have a non-selective trip. Coming on to that is a huge safety margin. So you can see here the safety margin in this case about 175 milliseconds. And then you say, but why? I could have made the zone 2 timer much shorter. Yes, you could, in theory, if that is the only consideration you have. Typically it is not done, okay? And probably one of the main reasons why one typically has longer time grading, okay, before I get on to the next slide to show that, is remember the zone 2 has another purpose which we sometimes forget, because it's just a little additional information. The zone 2 has the function of remote backup. So what does it mean, remote backup? Remote backup and the distance protection generally does a very, very effective remote backup functionality. Remote backup is that if this fault that we are seeing here fails to be cleared, if the relay at the top, that's zone 1, that relay is does not pick up, maybe it's VTS failure, or maybe its contacts are breaking, or maybe the trip coils are broken, or maybe the DC has failed, or something goes wrong in a station there, and that protection fails to clear that fault. That's where the zone 2 then comes in. The zone 2 will then clear it here. When the time delay expired, it will trip as a so-called remote backup functionality. Okay, that is something one must remember. And that is why one also needs that's not the primary purpose of zone 2, it is a secondary purpose of a zone 2 to do that. In this remote backup functionality, it can be that the remote backup must be graded with a local backup. You think, what is a local backup? And you can see in the name at the top already, the breaker failure is a typical example of a local backup. And now we've taken the same time grading condition that we had before, but we have included the breaker failure at the top. So let's have a look what happens now. We have the same fault inception. The zone 1 at the top gives the trip command, but there is a breaker failure. The breaker failure is a local backup. It's a local backup, and it will try and now clear this fault locally in that substation. It needs a certain time, because that local backup at the top must also be checked. Not that it trips the bus bar, the breaker failure, before the zone 1 has chance to open the breaker. So there's a time grade, typically 120, 140 milliseconds. That's the typical breaker failure time, in which you allow that breaker at the top to clear. If it hasn't cleared after 140 milliseconds, then the breaker failure will issue a breaker fail trip, the so-called T2 time trip, we call it, the breaker fail T2 trip, and that will typically clear the bus bar. Again, you need some circuit breaker time, because now this is going to be the circuit breaker time after the breaker failure trip. And you can see that would then reset around here. So if we then take that time point over here, we don't want our zone 2 to interfere with the remote backup, okay, to trip there, because maybe the fault can be cleared. Maybe there are 2 bus sections at the top and the breaker failure can clear the bus section. And if we trip, we may trip off the second bus section, which was still in service. So we need to make sure that our zone 2 does not interfere with the breaker failure. So we need to set our time grading step longer than that. And in this case, you can see the 250 milliseconds is still okay, but the safety margin is now significantly smaller, about 55 milliseconds in this calculation technique, but that would be sufficient. So that's the reason why one needs a time grading step. And typically this time grading step is then applied throughout the system. As you go through a next stage that needs to be graded with that, you increment by 1 time grading step as such. And this time grading step is therefore typically defined for a complete interconnected system.